Hello, this is Professor Kuehn, and welcome back to my lectures on space, time, and motion. We are beginning into Chapter 11 in A Student's Guide to the Great Physics Text, Volume 2. This chapter is titled From Conic Sections to Projectile Motion. So let's get started. What I'm going to do is I'm going to begin by reading some selections from the bottom of page 141. This is the fourth day of the dialogues between Salviati and Segredo and Simplicio. So it begins with Salviati reading a short section of the book that they've been looking at. So this is Salviati essentially reading from Galileo. He says, "In the preceding pages, we have discussed the properties of uniform motion and of motion naturally accelerated along planes of all inclinations." So that's the last couple of chapters that we've been studying in this course. "I now propose to set forth those properties which belong to a body whose motion is compounded of two other motions, namely, one uniform and one naturally accelerated. These properties, well worth knowing, I propose to demonstrate in a rigid manner. This is the kind of motion seen in a moving projectile. Its origin I conceive to be as follows." He goes on the next page to say, "Imagine any particle projected along a horizontal plane without friction. Then we know, from what has been more fully explained in the preceding pages, that this particle will move along this same plane with a motion which is uniform and perpetual, provided the plane has no limits. But if the plane is limited and elevated, then the moving particle, which we imagine to be a heavy one, will on passing over the edge of the plane acquire, in addition to its previous uniform and perpetual motion, a downward propensity due to its own weight, so that the resulting motion, which I call projection, projectio, is compounded of one which is uniform and horizontal, and another which is vertical and naturally accelerated. We now proceed to demonstrate some of its properties, the first of which is as follows." So what is he doing here? He's saying he is going to be talking about not simply uniform motion and not simply uniformly accelerated motion, but objects which undergo a combination of both. And specifically, he's going to say projectiles, or artillery, you might think about it that way, experience projectile motion, which is a combination of uniform horizontal motion and naturally accelerated vertical motion. And as an example of this right away, he says, imagine you have this, you might think about a plane or a cliff, and an object moving along this cliff, a ball rolling, and neglecting friction, once again, we would imagine if it's doing that, it's going to keep moving in a straight line at a constant speed. It's going to be undergoing uniform motion. But when it gets to the edge of the cliff, what's going to happen is it's going to fall off the cliff. But as it's falling, he's going to claim that it's going to continue moving horizontally with uniform motion, but it's going to also acquire a naturally accelerated or uniform acceleration downward. Let me jump ahead 2 pages. There's a diagram that illustrates this, and he's going to come back to this later. So if we go to figure 11.3, you might imagine that the line segment AB on this diagram represents the top of this cliff. So we're looking at the cliff from the side, and then the line segment BOGLN is kind of the vertical face of the cliff. And if you have an object that is moving along AB at a uniform speed, it gets to point B, and at that point, it falls off the cliff, and it's going to follow this trajectory, and he's going to argue this is a parabolic trajectory, and that's compounded of a uniform horizontal motion, and then also on top of that, a vertical motion that is uniformly accelerated, so it's going to fall downward. So he's going to refer to this diagram later on. Let's go back to the text, okay? So what he says is that he's going to demonstrate some of the properties of this motion that this projectile undergoes, the first of which is as follows, and here he says Theorem 1, Proposition 1. A projectile, which is carried by uniform horizontal motion compounded with a naturally accelerated vertical motion, describes a path which is a semi-parabola or half parabola. Okay? Now, after having defined this, now you have Segredo and Simplicio chiming in and offering a few comments. So I'll go ahead and read these because these are kind of fun to read, and I'll comment on them as I go. Segredo says, "Here, Salviati, it will be necessary to stop a little while for my sake, and I believe also for the benefit of Simplicio. For it so happens that I have not gone very far in my studies of Apollonius, and am merely aware of the fact that he treats of the parabola and other conic sections without an understanding of which I hardly think one will be able to follow the proof of other propositions depending upon them." So he's talking here about, there was an ancient Greek mathematician named Apollonius, and he wrote about what are called the conic sections. And the conic sections are, if you take a cone and you cut it in different ways, it forms different curves. And this was a standard geometry textbook. And Segredo saying, whoa, wait a minute. I haven't read Apollonius in a long time, so if you're going to be claiming that this thing undergoes parabolic motion, and I remember from Apollonius that a parabola is one of the conic sections, I'm going to have to review this before you get into it. Otherwise, there's no way I'm going to follow what you say. He goes on to say, since even in this first beautiful theorem, the one that Galileo just put forward, the author finds it necessary to prove that the path of a projectile is a parabola. And since, as I imagine, we shall have to deal with only this kind of curves, it will be absolutely necessary to have a thorough acquaintance, if not with all the properties which Apollonius has demonstrated for these figures, at least with those which are needed for the present treatment. So we're going to have to remind ourselves what these conic sections are. Salviati comes back and says, okay, you are quite too modest, pretending ignorance of facts which not long ago you acknowledged as well known. I mean, at the time when we were discussing the strength of materials and needed to use a certain theorem of Apollonius which gave you no trouble. So Salviati is saying, wait a minute, you're being too modest. I know you understand this stuff because you agreed with something I said earlier when I mentioned Apollonius and you seemed okay with it. And Sagredo then replies, he says, I may have chanced to know it, or may possibly have assumed it so long as needed for that discussion, but now when we have to follow all these demonstrations about such curves, we ought not, as they say, to swallow it whole and thus waste time and energy. So he's saying, well, maybe at that time I said, yes, I understand, but maybe I didn't really understand. I was just kind of playing along because I didn't want to slow down the discussion. So I went along with it then, but now it's coming up again. We better actually deal with this and make sure I understand what you're talking about, okay? And then Simplicio chimes in. He says, now even though Sagredo is, as I believe, well equipped for all his needs, I do not understand even the elementary terms. For although our philosophers have treated the motion of projectiles, I do not recall their having described the path of a projectile except to state in a general way that it is always a curved line, unless the projectile be vertically upward. But if the little Euclid, which I have learned since our previous discussion, does not enable me to understand the demonstrations which are to follow, then I shall be obliged to accept the theorems on faith, without fully comprehending them. So he says, now, I've studied a little bit of Euclid. You might remember Euclid is another Greek geometer. And ever since we've been having these discussions, I've gone back and read some Euclid. But I'm going to be lost if we don't get a better handle on the conic sections in Apollonius. And so Salviati comes back and says, on the contrary, I desire that you should understand them from the author himself, who, when he allowed me to see his work of this, was good enough to prove for me two of the principal properties of the parabola because I did not happen to have at hand the books of Apollonius. These properties, which are the only ones we will need in the present discussion, he proved in such a way that no prerequisite knowledge was required. These theorems are indeed given by Apollonius, but after many preceding ones, to follow which would take a long while. I wish to shorten our task by deriving the first property purely and simply from the mode of generation of the parabola and proving the second immediately from the first. So he's saying, well, frankly, we don't have to go back and open up Apollonius and start reading through all of his propositions because it's long and tiresome. It's going to take too much time. So the nice thing is this book that we're looking at together, the author has kindly presented two proofs, and these are really the only ones we're going to need. So we're just going to review these. Okay? And then what Galileo does here is he goes on to present the proofs of the properties of parabolas. Now, I'm not going to go through these in detail. What I want to do is I want to just remind you about the conic sections, first of all, and then highlight some of the main things that Galileo is saying here. So you might remember the conic sections. So I'm going to draw these over here. And these date back, as Galileo mentions, to the work of Apollonius. So first of all, let's suppose that we had a cone. Draw a cone like this. And let's suppose we were to take a plane and we were to cut the cone by this plane so that the plane is parallel to the base of this cone. In so doing, the line of intersection of the plane with the cone would form a particular line, and this line would be a circle. So that would be one of the conic sections. That is formed when the plane of intersection is parallel to the base of the cone. Or you might say it's perpendicular to the axis of the cone. Okay, that's the first conic section. Okay, what about the next conic section? I'll draw another cone. What if I were to take this plane and cut the cone at a funny angle, at an oblique angle like this? Well, if I were to do this, it would, again, the intersection would form a line like that. And this line, you guessed it, maybe, is an ellipse. This is the second of the conic sections. And this is if the plane is tipped, roughly speaking. We'll have to qualify that a little bit in the next couple of examples. So if it's tipped, then the intersection will form an ellipse. Okay, 2 more to go. Here's another cone. Well, this one's, I guess, a little bit wider cone in my drawing. What if I were to take this plane and cut it like this in a way so that this plane was was parallel to one of the sides of the cone. So this side right here, this right side of the cone, the plane is parallel to that side of the cone. And if I do this, then the intersection line will be what is called a parabola. That would be if the plane is parallel to one side of the cone. Notice that I could have cut it in a lot of different locations, but as long as I'm parallel to this side, then I will have formed a parabola. Okay, and one more. Each of my cones looks a little bit different, I suppose. Now, what if I were to cut the plane more vertically? So I were to take this plane like this and cut in this way, so it's at a steeper angle than the side. If that is the case, then I will form what's called a hyperbola. That is, the plane is tipped more than for the parabola. Then it will form a hyperbola. And you might, this might look a little bit foreign to you. You've probably seen 2 cones stacked on top of each other, the top one inverted compared to the bottom, and the parabola is 2 lines that look kind of like horseshoes with their curved edges toward each other. Well, that is what would happen if I were to put another cone on top of this one. This plane that's cutting the one cone on the bottom would also cut the cone that's stacked on top. But if, like with the parabola, the plane is tipped so that it's parallel to one face, it actually will not cut the cone that's on the top. That's why it's a parabola. So really, if you have a tipped plane, you form an ellipse if it's a very small slope plane. And if it's tipped a lot, then it's a hyperbola. The parabola is really a edge case or a borderline case between the ellipse and the hyperbola. It's being cut by a plane at a specific angle so that that plane happens to be parallel to one of the sides of the cone. Okay, so that's a review of the 4 conic sections. And by the way, these show up here the parabola shows up in Galileo's work on projectile motion, but the conic sections play an important role also in the motion of planets or comets. They're going to play an important role in the work of Isaac Newton when he's exploring the force of gravity, and we're going to find that the orbit of the planets around the sun is going to follow these conic sections as well. And it also is going to show up later on with the work of Rutherford. We won't talk about that in this class, or more generally scattering of particles off of each other. We're going to find that the trajectory of these particles is a hyperbolic motion when it's a repulsive force. Okay, now let me just say a couple of other things and I'll stop. So what he does here is he demonstrates, what Galileo does on page 143, this proof, is he demonstrates that if you cut a cone by a plane so that the plane is exactly parallel to one of the faces, then you will get a parabola. And how does he do that? He shows here a cone, FIK, and he shows a situation where it is cut. And you can see this cut is kind of the intersection. That cut is represented by the line B, or the curve BAC. And what he's going to do is he's going to show that that curve BAC has the characteristics of what we call a parabola. And specifically, if you look at the bottom of the long paragraph in the proof, he says that the square, and this is what he's trying to get at, the very last sentence is, the square of BD is to the square of FE as the axis DA is to the proportion AE. In other words, in his proof, he is going to try to show that BD, the square of BD, so take the line segment BD, and I square that, is to the square of FE, FE squared. So BD and FE, the ratio of the squares of those is in the same ratio as DA, the line DA, is to the line AE. Okay, and he says, because when I cut it in this way, he shows that this is the case, because when I cut it in this way, this formula holds, that implies that this is a parabola. Now, this might not look like the proof of a parabola to you, but what if we were to write this as y2 is to y1 as x2 squared is to x1 squared? Or if I were to write that he has just shown that y is proportional to the square of x. That is essentially what he's doing here. So if I were to take this curve and I were to turn it upside down, I'm running out of space here, so let me move this over to here. If you were to take this curve and turn it upside down, you'd see exactly what he's talking about. And if I were to call this the x-axis and this the y-axis, and I were to call this point A right here, and this point D right here, and this point right here, we'll call that point E, and we'll call this line segment right here EF, and we'll call this line segment right here DB. This right here is a parabola because the displacement along the y-axis is proportional to the square of the displacement along the x-axis. That is, if you take this point right here, that is at position y2, x2, y2. Let me rewrite that. It's at position x2, y2. And you consider this point right here, which is at position x1, y1. Well, x2 would be the line segment A, I guess, the x2 would be the line segment DB, and y2 would be the line segment DA. And so you can see here in this formula right here is basically saying that y2 and x2 squared right there, and then the line segment EF would be x1, or FE would be x1, and the line segment AE would be y1. And so y1 is to, or y2 is to y1 as x2 is to x1 squared, which is precisely what we mean by a parabola. You've probably seen this more commonly as y equals ax squared, where we're saying y is proportional to the square of x. That's a parabola, and that's basically what's happening right here, that y is proportional to the square of x, or as he says it, dA is to AE as BD is to FE squared. Okay, so the point there is he's just reminding us of how you construct a parabola and the relationship between the x and y coordinates that make up a parabola.